Eigenvalues and eigenvectors. Yeah, I know. If those words from linear algebra sound a little intimidating or just way too abstract, you are definitely not alone. But what if I told you they were the key to understanding the absolute essence of a transformation? Today, we're going to pull back the curtain and demystify them, starting with a really powerful idea. Our source material kicks things off with this fantastic analogy. Eigenvalues are the DNA of a matrix. Now, that's a pretty bold statement, but you know what? It's incredibly accurate. It's telling us that these special numbers hold the deepest secrets about what a matrix really does. Okay, but what does being the DNA of a matrix actually mean? How can just a few numbers reveal the core behavior of this whole complex transformation? Well, to get there, we first need to see what a matrix normally does to a vector. All right, section 1, matrix DNA. Let's build up the big idea, that core intuition, before we even touch a single equation. Think of a matrix like a transformation machine. You feed a vector in, and it gets pushed, pulled, sheared, maybe rotated. Something happens to it. For almost any vector you could possibly choose, this transformation is going to change its direction completely. It gets knocked right off its original line. So while most vectors are getting spun around and sent in all sorts of new directions, there's this exclusive club of vectors. These are the eigenvectors. They are special because they're incredibly stubborn. They resist this change in direction. See, when an eigenvector gets hit by the matrix, it stays right on its original line. It doesn't get knocked off course at all. The only thing that changes is its length. It just gets stretched or maybe shrunk. This direction is invariant. It's fundamental to the matrix. So now that we have that gut feeling for what's going on, let's see how this whole concept is captured with math. And honestly, it all comes down to one beautiful, elegant equation. And here it is, a times v equals lambda times v. Let's break that down. On the left, AV is the transformation. It's what the matrix does to the vector. On the right, lambda v tells us the result is just the original vector v, but it's been scaled by some number, lambda. And that number, lambda, that's our eigenvalue. It is literally just the stretch factor. So, the big question is, how do we find these critical stretch factors, the eigenvalues? Well, the process is kind of like a two-step hunt, and it starts with finding lambda. First, we form what's called the characteristic equation. It looks a little scary, but all it says is the determinant of A minus lambda times the identity matrix I has to equal 0. Once we have that equation set up, we just solve for lambda. Let's see it in action. All right, let's get our hands dirty. We're going to use this 2x2 matrix as our test subject. Our mission? Find the special stretch factors, those eigenvalues that are hidden inside. Okay, step 1 is to build that characteristic equation. We take our matrix A and we just subtract lambda from the elements on the main diagonal. Now we need to find the determinant of this new matrix and set it all equal to 0. So the determinant of a 2x2 matrix, that's just the product of the main diagonal minus the product of the other one. So that gives us 3 minus lambda squared minus -1 times -1 equals 0. And now it's just a little bit of algebra. Let's expand that out and simplify. And look at that. We land on this nice, clean quadratic equation. This right here is called the characteristic polynomial of our matrix. Now here's the crucial part. The roots of this equation are our eigenvalues, so all we have to do is factor it, and we can find our two solutions. And from that first factor, we get our first eigenvalue. Lambda is 2, the first piece of our matrix's DNA. This means there is a special direction out there that this matrix only stretches by a factor of 2. From the second factor, we get our second eigenvalue, 4. This tells us there's another special direction, and vectors along that line get stretched 4 times as long. And just like that, we found them. Okay, so now we have the what. We've got the stretch factors. But now we need to find the who. Which specific vectors, or which directions, actually correspond to these eigenvalues. And the process is pretty simple. We take each eigenvalue one at a time, we plug it back into the equation, a minus lambda I v equals 0, and then we just solve the resulting system of equations for the eigenvector, v. Let's start with our first one, lambda equals 2. We plug it into our a minus lambda I matrix, which gives us this new matrix here. Now we're looking for a vector v that this matrix sends to the 0 vector. So When we perform the matrix multiplication, that top row gives us the equation v1 minus v2 equals 0. The bottom row gives us negative v1 plus v2 equals 0. Hang on. Notice something? They're the exact same equation. This is a really good sign that you're on the right track. It simply tells us that v1 has to equal v2. This means that any vector where the first and second components are the same is an eigenvector for lambda equals 2. It defies an entire line of vectors. We just need to pick a simple non-zero example, so let's go with 1, 1. And hey, if you were to do this exact same process for our other eigenvalue, lambda equals 4, you'd find its corresponding eigenvector is 1, negative 1. Each eigenvalue has its own special direction. So far, so good, right? Everything has been pretty neat and tidy. But what happens when the math takes an unexpected turn? What if our characteristic equation doesn't give us those nice real number solutions? So just imagine for a second, you go through this whole process, and your characteristic equation simplifies down to this: lambda squared plus 1 equals 0. If you try to solve this, well, you run into a problem. There are no real numbers that, when you square them, give you negative 1. Here, the solutions are imaginary numbers, positive and negative times I. So what on earth does that mean? Well, complex eigenvalues almost always correspond to a rotation. And think about it, it makes perfect sense. If a matrix's whole job is to rotate every vector, then no real vector, other than 0, is ever going to end up pointing in the same direction it started. It makes perfect sense that there are no real eigenvectors. So we've decoded the matrix's DNA. We have its eigenvalues and its eigenvectors. And this isn't just some abstract mathematical exercise. In fields from physics to finance, these values predict a system's long-term behavior. An eigenvalue greater than 1, that might signal exponential growth. A complex one could describe a stable oscillation. By finding this DNA, we unlock the ability to actually predict the future.